What up, everyone? This is Mr. Jennings, and today on Big Orange Biology, we're going to talk about thermodynamics. Now, thermodynamics is a critical aspect of biology, and it's based on this concept in chemistry about how energy moves throughout an ecosystem and through systems in general. So, class is now in session. Let's get rolling. So, we're going to talk about energy today, and energy, we need to understand, is the capacity to cause change. This is a little bit of a physics term, and really what that means in biology is it's the ability for energy to cause change in organic systems. Now, energy can exist in various different forms, some which can be used to perform work, or they can be converted from one form to another to make work. Various forms of energy exist, like kinetic energy, potential energy, chemical energy, nuclear energy, electrical energy, thermal energy, radiant energy, so on and so forth. Now, kinetic energy is one of the main ones we like to discuss. That is the energy associated with motion. We kind of touched upon that when we discussed kinetic molecular theory in lecture during class. Now, kinetic energy, is, like I said, energy associated with motion, and we measure kinetic energy by measuring heat. Because the idea is that the more heat or thermal energy an object contains, the more kinetic energy those particles will have. And we see that when you take a solid like ice, and you apply more heat to it, it gains more energy and it eventually melts. And if you keep adding heat to it, the energy gets so much more energy, it overcomes the intermolecular forces that make it a liquid to become a gas. And it gets even crazier when you go into plasma. Now, potential energy is energy that matter possesses because of location and structure. It's the potential to cause change. That is what really potential energy is. And one form of potential energy we like to look at is chemical. Now, chemical potential is the energy found in chemical bonds that are available whenever a chemical reaction occurs. So, to give you a visualization of a potential and kinetic energy situation, think of a diver sitting in front of a lake. Now, as the diver goes to jump off the diving board, he has tremendous potential energy because they're at the top of the diving board. They're full of energy. And as they jump off, that potential energy is going to convert into a movement. And that movement's going to be called kinetic energy. And as the diver falls into the water and makes that big splash, the diver has now lost his kinetic energy into the water, but also has very little potential energy. Now, once the diver gets back on land and starts climbing these stairs again, he's going to exert kinetic energy. That motion is going to allow him to travel up and gain potential until he reaches the top, where he has all the potential energy in the world, or all the moment he can have at that time to jump off again. So it's a cycle. One feeds into the other. And understanding how energy feeds into other energy systems is thermodynamics. That's how energy transforms. See, we can look at systems in two ways. We can look at it in a closed system, like liquids in a thermos. Thermoses are isolated using a vacuum tube, and they don't, lose heat very well. That's because of the vacuum that exists between them. It's isolated from its surroundings. Now, not very many things we're going to find here on Earth are closed. The Earth itself is sort of a closed system. The atmosphere kind of keeps everything in, but we do lose a little bit of the atmosphere to the space, and space can interfere with us. So we really classify more as open systems. Now, open systems are where energy and matter can be transferred between the system and its surroundings, and it goes back and forth. And all living things are considered open systems, as are most planets. Now, like most things in chemistry and physics, there are laws to help explain how thermodynamics works. Now, laws in science are not like laws of humans. Laws of science are basically a series of very specific explanations for very specific scenarios. It will tell you what will happen in a very specific situation. So, one of the first laws of thermodynamics, is the first law of thermodynamics, is that energy of the universe is constant. That energy can be transferred and transformed, but it cannot be created or destroyed. Most of us do know that. It's a common thing taught in elementary school. You just never heard of it as the first law of thermodynamics. Well, now you know what it is. You probably learned it more as the law of conservation of energy, and it's got a very similar cousin, the conservation of mass. And that's because of Einstein and gets into some other complications. So we need to keep in mind that all the energy of a system is connected. It is transferred from one form to another. And that means all the chemical reactions found in a metabolic pathway are connected somehow. All the energy that's going to move between these chemical reactions. Now, second law of thermodynamics is one that you probably don't know, but you have seen it and you do experience it every day. Second law of thermodynamics is that energy transfers or during energy transformations or transfer, a little bit of that energy is going to go and destabilize something. That is called entropy. See, order is not desired for the universe. Order is enthalpy. It takes a lot of effort to maintain something in order. Entropy is disorder or chaos. As the universe continues to exist, disorder will increase. That's the second law of thermodynamics. Disorder will always increase, and it has to increase. Now, some of this is because the energy is unusable during energy transformations. Remember, you may have learned in ecology and general biology that only 10% energy is conserved between trophic levels. Well, the other 90%, it just doesn't disappear. It's transferred in the form usually of heat. Well, that heat heats up the surrounding ecosystems and surrounding particles found in it, and as those particles heat up, they move faster. They go from order to disorder. Now, to make a really good understanding of how order and disorder works, look here at this picture of the toss brick. If I throw a bunch of bricks off a truck, which is likely to happen? Would it make a nice stack or make a crazy chaotic? It's going to make a pile more often than not. It's very unlikely it's going to make to maintain the order of a stack of bricks, it will require energy and effort. Maintain disorder requires no effort. It goes with the flow. It's from high concentration to low concentration. And you think of a bedroom. Bedrooms are just if you don't clean up after yourself, they tend to just get messy. It takes effort. That brings us to what organisms really act as. See, organisms, they are highly ordered. So they do not at one point you think, man, we always stay in order. How are we not disobeying the laws of thermodynamics? Well, we're not. Organisms follow the law of thermodynamics because we are energy transformers. We are the conduit which energy transforms from one form to another. We are chaos incarnate. Our mere existence creates more chaos. We are highly ordered chaos engines because we're full of spontaneous reactions. We have spontaneous processes that require zero energy. We can all of a sudden ignite and have something take place. There's a ton of them. Usually we don't see a lot of them in organisms because they're dangerous, but we do have them. Most reactions though require a little bit of energy, and it will increase the entropy of the universe as a whole. So as we obtain energy, increase our energy input, as we obtain energy, we'll cause disorder. And for energy, without energy input, to be able to be spontaneous, we have to make it so spontaneous release is energy as well. Now, this equation here, don't get too hung up about learning every bit of this. It's just explaining where this comes in. So we looked at what's called free energy or Gibbs free energy. That can tell you how and when reactions happen. Essentially, reactions that have a negative delta G are considered spontaneous. And these are what's going to be used to harness work because they require little effort, little input, and the energy release can be used to transform other systems. Used to, in AP Biology, you had to know how to calculate that. That has been revised out of the rubric, out of the standard. Now, it is in your best interest to know what are exergonic and endergonic reactions. So, in second law of thermodynamics, basically it's all about order. Order becomes chaos. Well, how do we quantify that? Well, exergonic reactions are spontaneous reactions that release energy. They are going to create chaos. They are chaos engines. And they go from high, reactants have more energy stored in them, high potential energy, low potential energy, but the energy that's lost is going to create free energy. That's energy now freed up for other systems. Endergonic reactions have a positive delta G. They take in energy. They absorb energy from the surrounding. They're non-spontaneous. Exergonic and endergonic reactions are going to be paired up. All right, now to wrap things up here. So we'd like to look at energy as a series of transformations or transferals. That's the idea of first law of thermodynamics. Energy cannot be created or destroyed. It's merely transformed or transferred. Now, the act of transferring energy leads into the second law. The second law states that the transferring of energy will result in order going into chaos, going from enthalpy to entropy. Now, that is going to be exemplified by the use of the free energy equation. As organisms increase their order, they require more energy, but they release energy in the process. But we have some reactions that are going to release free energy. So spontaneous reactions are the ones that do that. Very little energy input, and you get maximum energy output. Doing that is fantastic. What we need to understand is that since energy cannot be created or destroyed, so reactions that require a lot of energy are often going to be coupled reactions that require no energy. So intergonic reactions, exergonic reactions in order to exist. So intergonic reactions are going to take the energy that's released, that negative delta G, and power the positive delta G reactions. Those intergonic reactions are going to get powered by exergonic. All right, now we're going to explore this a little bit more. We're going to, in lecture, we're going to talk a lot about ATP and its role in this process. Turns out the synthesis of ATP is going to be one of the most important things we're talking about. We're going to talk about the synthesis of ATP and hydrolysis of ATP. And the mere action of it forming and breaking all the time is going to be the major driving force of our cellular energy. All right, I'm Mr. Jennings. I hope you had an excellent day.